Sorry, there's absolutely no question that I should have changed batteries when I looked for my minus sign mistake. Whoops! Okay, so we want to talk about what the R-square is doing in here in this Jacobian determinant for going from Cartesian coordinates to spherical coordinates. And that has to do with what volume truly is for spherical coordinates. What volume is it's the volume of a hollow sphere of radius r. And a volume of a hollow sphere is the difference between this sphere's, what do I mean? Oh, surface area. The inside surface area and the outside surface area. That thickness multiplied by some dr, this surface area multiplied by some dr, is actually the volume of a sphere of some radius r. Not a sphere, but a hollow sphere. So we have an r squared there that says as we get larger and larger ara, like this sphere then would have this volume that's in some chunk right here where we differentially change theta and we differentially change phi and differentially change ara. There's more volume contained there simply because we've got ourselves spread now over a much larger sphere, hollow sphere, so that hollow sphere has more. This is really awful. Is this making any sense at all? What I'm saying is the volume increase as we go to larger and larger r is proportional to r square. That's this r right here. Square is proportional to r square because it has to do with the surface area of the hollow sphere at which you're doing the volume calculation. Now, of course, you gotta have two more orthogonal directions. There's gonna be a d theta direction, which in this case would be oriented like that, right? And there's gotta be a d phi direction, which is gonna be oriented like that way into the page a little bit. But there's an orthogonal direction of d ara, and d ara is that last dimension that I absolutely can't draw right there. But that's how you get volume out of just the r squared. Anyway, I hope this makes a little bit of sense to you, and you can put your best explanation of it into the comments, and maybe I'll make this video again when I make some more sense with my words. But you've seen it mathematically, and now maybe you have a little bit of justification for what this term is doing right here. It's making sure that you're weighting farther out sections because the spheres have more surface area at that point by r squared. Bye. Hey, today we're going to do a little bit of mathematics, but don't worry, it's mathematics that is necessary to understand quantum mechanics and various other things in physics that you might encounter that happen in 3 dimensions. So a lot of times I get people asking me, why is the differential volume element, why does it have these two things in here? See these two funky things right here? It's not just dr, d theta, d phi. And before we go into this, I need to tell you that I'm going to use the physics convention, which, well, I'll talk about it as I draw it, but I wanted to show you how I draw it so that you can get some tips on drawing it as well, because if you're going to be taking notes on this stuff, anything in 3 dimensions, you're going to want as much help as you can get with this. It's not entirely obvious how you can do this effectively. So one usually begins by, whatever, I'm not going to say usually, this is the way I begin. You define the x and y plane as being kind of out of the paper, slicing through the paper where the y-axis appears on the paper. So I'm going to show the x direction coming out at us like that. You've got to imagine that's a vector at your face. So put it up really close to your face and you can look down that vector a little bit. And then we need to determine what it is we're mapping out. So there's going to be some location, some point that we'll call probably P, because that's where stuff usually is. So here's our vector that indicates the point P in space. There's the location P. And you know, when you grew up, you knew that P has some coordinate values. It has some location in X and in y, and in z. And now you are hanging out with people who are telling you, sometimes very angrily, that you need to be able to tell them where it is in terms of some other coordinates. So let's define those coordinates. First thing to note is that z is special. The xy plane, not special. Z, special. Is pointing up. I don't know, it's kind of like cylindrical coordinates. Z is special there too. But I gotta tell you that I'm going to be using the physics convention which is not consistent with polar coordinates. Because in polar coordinates, in the xy plane, there is a theta. But I've taken theta and I've moved it up here to z. So it's sometimes called the, what would you call it? Oh gosh. Well, I don't know what you'd call it, but the other angle that we're going to have down here could be called the azimuthal direction, the azimuthal angle. So let's take a dotted line. Now this dotted line is going to be parallel to the z-axis. So that's how you do this next part here. What should I do? Oh, guess I'll do it in green. That's fine. So I'm going to end when I believe that this line crosses through the xy plane. Now remember, the xy plane is out of the screen, so I'm going to declare kind of arbitrarily that it ends here. That's where it crosses the xy plane. So I can make a dotted line in the xy plane. It's going to go from here to where the line parallel to z crosses the xy plane. So that's this line right here. And of course, this dotted line right here in the xy plane is normal to a line parallel to the z-axis. So I'm going to show that it's normal by drawing a little square that looks like that. That is the designation that those two are normal. So can you imagine? Can you kind of see the three-dimensional nature popping out here? Okay, well, there's of course the length ara. That is the distance from the origin to your point P. And everybody knows that ara is related to x and y and z. It's probably the square root of quantity x squared plus y squared plus z squared, right? And there's another thing here. There's this other angle that we'll need to specify. And once we've specified how far out we are in absolute value, and we've specified how much we've gone down from the z-axis, then we'll need to also specify how far we've gone over from the x-axis. Now notice it's going that direction from the x-axis, so we could have negative of these angles here, which we're going to call phi. But, let's talk about the bounds of these. I mean, if we're really just talking about spherical coordinates, then the bounds of these things are really important. First of all, ara cannot be, it cannot be less than 0. What would that even mean? You'd want to change the angles instead of calling ara less than 0. So we've got ara going up to infinity, arbitrarily large, but capped on the bottom end at 0. And then what about theta? It really wouldn't mean anything to go past the z-axis that direction. I'd rather just measure theta that way to do that. So I'm going to call theta is going to be bounded between, what do we say? And oh, we don't really want it to get there if theta, well, no, okay, we can let theta get there. We could let theta get up as high as pi. It's not going to be able to go all the way around, but we'll trap it when it gets all the way down. But then phi is going to be allowed to take us all the way back to the x-axis. So I guess if I were to use the consistent language, theta is going to allow us to get to the negative z-axis. Phi will allow us to go all the way around, and then we've mapped out all of 3 space right here. We have the entire volume mapped out. So we can, what are we going to let? We're going to let phi go between 0 and 2 pi. Okay, so when we're doing integrals, we need to use those limits and in order to get over all of space. But that's not the subject of this discussion. The subject of this discussion is when you're doing an integral, why do you get this term, this r squared sine theta dr d theta d phi? And that's equal to the third derivative of the, the differential space element, not the third derivative, but the differential element of where the dang thing is. So, of course, you want to take the determinant of the Jacobian matrix. If this doesn't mean anything to you, then you can skip to the end where I'm talking about what this means. But for now, let's just do a whole bunch of math. We know that, by fiat, the differential volume element is going to be, we need to take the, let's see, we got your x and your y and your z, right? And we need to take the partial derivative with respect to r and theta and phi. So we're gonna have to define r and theta and phi, or rather let's define x and y and z in terms of r and theta and phi. And then we'll take that Jacobian determinant and then multiply that by dr, d theta, and d phi. Okay, so getting that is going to be really fun. But let's see, maybe on this page we can also do, no, it'll be actually helpful to have it on the next page. So you've got those things written down, so let's go to the next page where we start to figure out, let's see, we can keep this over here, but we need to figure out what x and y and z are. How could I get x and y and z by knowing r and theta and phi? So this is part of the coordinate transformation. X, let's see. In order to get x, you know what's actually going to be really easy? Let's do z first, because remember z is special. If it makes you uncomfortable that z is special, remember always that z is not special. You can orient z any direction you want, and then it'll just redefine what z is, and then you can do your theta and your phi from that new z. In the case of having a magnetic field, for instance, we're going to always orient z along our magnetic field direction. So it's ready to do whatever you want it to do. It's not a special direction oriented before the problem, but rather as you do the problem, orient z in the direction that makes sense. Kind of like how we orient the normal force as our y-axis when we're like doing simple ramp problems. But z is special, so what I can show you is that how high you are up in the z direction, that would be, I'm going to do a dotted line that's in the xy plane, and it's probably going to have to go like, oh gosh, it's probably going to have to go like this. Where this is a right angle, of course. We've got a right angle here. That's a right angle. And this distance right here is just going to be r times, what do you got there? You got the cosine of theta, right? That's that distance that the point P is up the z-axis. So that gives us our z component. We're just going to write r times cosine theta. Oh, did I tell you that this is ISO specification? I actually have that ISO code. It is ISO 80,000, that's a whole bunch of zeros, -2:2009. So you can look it up, mathematicians. You want to do it your way, which is more consistent linguistically? Fine, but we got ISO specification in physics, sucker! So I kind of have some regret about that. I'm sorry that I was so mean. The other ones, though, the x and y components are not going to depend on how high it is up the z-axis, but rather how much it is into the xy plane. This quantity right here is going to be r, that's this length right here, which is the same as this length right here. So let's talk about that. That's just going to be r sine theta, right? This is r sine theta. That's the distance that actually, if we were doing just regular polar coordinates, that would be our r value. It's just r sine theta. That's how far it is along this distance to the point that is maybe the shadow of the P location if we're looking, shining a light from in the z direction down, the negative z direction. There's our shadow, and that's r sine theta. So both of these are going to have an r sine theta, and they're just going to be r sine theta and r sine theta, and then we just have to multiply those by something having to do with oh, what's that guy called? Oh yeah, phi. So I want to go normal to the x-axis here, and I'm going to pull out a vector this direction. Oh my goodness. Is this going to make any sense at all? No. Let's go, let's force it to be normal in that direction, but go parallel to y. Here we go. This is making a little bit more sense. And this vector, there, that is normal. Just disregard that guy, that failed attempt right there. This vector now has a hypotenuse, this triangle here has a hypotenuse of r sine theta, and this side right here, which must be the y value, ooh, it should have been, oh no, I can draw it over here. Good, this is another right angle. So here's that triangle again, but the angle's at the other side, so I'm not going to draw that one. But this guy right here is just r sine theta. That's the hypotenuse's length times, what do you have? The sine of phi. And then over here, you've got r sine theta times the cosine of phi. So that's our, oh gosh, that's what the x direction is, r sine theta cosine of phi. And our y direction is r sine theta sine phi. So it's time to take the determinant of the Jacobian. So in order to take the determinant of the Jacobian, we better write the Jacobian. I'm going to be taking the derivative of these guys in a certain wonderful direction. Let's take it like, oh, let's use a different color. How about brown? We have a large matrix. And that large matrix is, it's really only going to be 3 lines. So I'm going to take the derivative of x with respect to ara, and then I'll take the derivative of x with respect to theta, and then the derivative of x with respect to phi. So let's say, oh, do you guys know what Jacobians are? Whatever, look it up. Here I am taking a Jacobian, and then I'll take the determinant of it. I'm going to take the derivative of this guy with respect to ara, so that's just sine theta cosine phi. And then I could take the derivative of this guy with respect to ara. That's really easy too. It's just sine theta sine, whoa, okay. All right, I'm going to make a million mistakes like this. You just got to let me know. Okay. And this guy with respect to ara is just cosine of theta. And then we're going to go boom, 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 and take derivatives of these guys with respect to theta. So then I get an r cosine theta cosine phi. And here I get, oh gosh, really similar, r cosine theta sine phi, and down here it's just going to be, wow, just ara times sine of theta, but it's going to have a minus sign up front. That's interesting, not really. And then this one, we're supposed to take the derivative of these guys with respect to phi. So wonderfully, I get a 0 right here. Let's celebrate that right now. Then over here, I'm going to get negative r sine theta sine phi. Ooh, I'm gonna have to close that sucker. Over here I get a positive number, r times sine of theta times cosine of phi, and now I can close this. We're going to take the determinant of this matrix, which is like this times the determinant of that matrix, plus this times the opposite of the determinant of that matrix, you know, all that fun stuff. So if we just label these guys certain things, we can shortcut it a little bit. Oh, this is going to be so miserable. You got your A, and your B, and your C, and your D, and your E, and your F, and your G, and your H, and your I. So if we're using this language, we want, of course, A times E times I, A, E, I, plus B times F times G, B, F, G. Then we want to add C times D times H and subtract C times E times G. Of course, minus B times D times I, and further subtracting A times F times H. A shortcut here allows us, oh, this is the determinant. The determinant of that matrix, the Jacobian matrix, is the following value. Jacobians are useful for translating from one coordinate system to another and taking into account the relative curvature of the two coordinate systems. We'll see at the end how this makes any sense. So we've got this messy thing right here, but anything that's got I in it is going to be 0. So let's circle those guys and kill them. And then we're going to have really a lot of fun. Let's take this first term, BFG. So it's r times cosine theta cosine phi, and then you got a little bit of f, which is r times sine theta. If I do anything wrong, we're completely doomed. We also have to multiply by h, which is minus r sine theta. Wait a second, that has too many r's in it. B, F, oh, sorry, then I need to multiply by G. I was on G right here. There, yep. Cosine theta. I know everything has to be r squared because I'm going to have always something from, if I've got, what am I talking about? No, you'd never get that, right? You're always going to have something from this column in the calculation. So we're always going to have squared power of r, or actually 0. But we've eliminated those. Okay, great, cosine theta. Let's go on. C times d times h. It's adding in minus r sine theta sine phi times sine theta sine phi. Whoa, wasn't that cool? And then multiplying in h, which then I'm supposed to still be multiplying these, minus r sine theta. Okay, 2 more terms. We've done that one and that one. Now I've got CEG, which is minus r sine theta sine phi. C times E, which is r cosine theta sine phi. We're supposed to have a G in there, which is just cosine theta. Oh, that's nice. It fit. Okay, and then this last term, we subtract A, which is sine theta cosine phi, times F, being r sine theta cosine phi. Oh my goodness. Then we got some h, which is minus r sine theta. So I had hoped, this is our determinant, I had hoped that we would have r squared in all terms, which means we can factor that sucker out. So let's see if that works. Let's see if that works to factor those suckers out. We got r squared, we got r squared, we got r squared, we got r squared. Okay, so I'm gonna say that this determinant is r squared times some stuff. This one we have cosine theta. I'm just gonna do the theta stuff first, and I'm gonna do sine and then cosine. So we got sine theta cosine theta, and then I have cosine squared of phi. Cosine squared phi. Next term, we have cosine theta. Oh, look, 2 cosine thetas. Cosine squared theta. Okay, but we don't have any sine phis. All right, this next term, we got a sine theta. We got 2 sine thetas plus sine squared theta. We've got, oh wow, sine theta. That's 3 sine thetas. We've got, look at all these sines. All of the sines hanging out together. We've got the sine squared of phi. All right, and then the next term, we've got sine theta and a cosine theta, and no, so 2 cosine thetas. Okay, so we probably should still go to the next line. I'm gonna have a plus sign out front with that one. I'm gonna have a minus sign left out front for this one. Minus, what do we say? Sine theta, just 1 sine theta, 2 cosine thetas. Sine theta, cosine squared theta, and then we've got sine squared of phi. Ooh, 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 look at this. Yay, this is really good news. Okay, and then this next term ends up being really complicated. We got 2 minus signs that are canceled. Oh, this subtraction. Are you kidding me? You've got to be kidding me. Oh, that was so exciting for just a moment. Okay, well, we'll just have to hope that I haven't made a terrible mistake. Let's see what happens. We're gonna have sine theta, sine theta, sine theta. We got 3 sine thetas, sine cubed of theta. And then, how about any cosine thetas? No cosine thetas, but I've got the cosine squared of phi. Oh, well, that's nice. Cosine squared of phi. All right, I'll close my parentheses and we'll look at this for a second. I hope we don't have to go back to here. I'm just a little bit worried that I'm missing a minus sign somewhere. I was hoping that this guy would be positive. This term is the 3rd term. CEG, C times E times G. We have no way of getting that sucker to be a positive number. This was the derivative of y with respect to theta. Nope. Okay, well, first simplification that I see is this is sine cubed theta times 1, right? But can we do anything cool about this? No! Why not? Oh, man. All right, well, let's factor out some stuff. This sine of theta is just sort of... Wait, there's a sine theta in everything, isn't there? Oh, that's nice. Let's factor out the sine theta and acknowledge the fact that these guys are... sorry, switching colors. We need to switch colors. All right, we got r squared... r squared times sine of theta multiplied by some stuff that's in parentheses. Let's see, the sine theta is gone, so I've got cosine squared theta times cosine squared phi plus, no, I took out the sine and I have the cosine and sine plopped together, so I've really got only left here sine squared of theta, right? That's this term and that term all together after I've factored out a sine of theta. And then I am subtracting sine, okay, sine theta is gone, so then I've got cosine squared theta sine squared phi. It kind of looks like there's like a cross term here. Is that possible? What should we do? Okay, I really like the structure here, but I can't deal with it. It's like cosine squared minus sine squared 1. Dang it, dang it, dang it, dang it. And then there's this sine squared right here. I may want to pause it and come back to you. I'm going to pause it. Ha! I found the mistake. I was really hoping that I could get rid of this minus sign right here, and I find out how I can get rid of it. But you gotta check me, because you don't want me lying at you. This is supposed to be minus c times e times g. I take minus c, and minus c is going to be positive, right? But I had written it in here as a plus sign. So I come in triumphantly with a plus sign right there. Check to see where that appears on this next line. It's supposed to be the third term. Third term is positive. I'm able to put a plus sign right here. Yay! This is really good news. Now I have cosine squared of theta times cosine squared of phi. I have cosine squared of theta times sine squared of phi. And everybody knows what happens at that point. Sine theta right here. And then this guy and this guy combine with the sine theta, cosine squared of phi and sine squared of phi being 1. So I get cosine squared of theta plus sine squared of theta. Yay! And so this is just r squared times sine of theta. That was really miserable. All right, now we're supposed to do something that has some sort of meaning. Y is, oh gosh, what do we do? We said something about the determinant of the Jacobian of the matrix. It was back here a little bit. We said once we got that determinant of the Jacobian, we would say dv equals, oh, let's do it on a new page because I want to talk about it a little bit. dv equals that Jacobian, which is r squared times sine of theta, times then dr d theta d phi. So if you're taking an integral over some volume, you need to multiply by this random looking plop plop right here. But let's get ourselves a little bit of sense out of this little plop plop. What is it? Hey little plop plop, what are you? Let's go back to this sketch right here, but I'll transfer it over and make it look a little bit nicer for a second. You've got yourself, we're going to try to do this a little bit faster, not talking as much. This is z, it's z, y, and x, and you've got some location p over here that you mapped to, and you need to go to some other coordinate system. So we define theta right here, and we have a dotted line. We trace this down. a dotted line right here at a right angle, and this being phi. We know two things. Let's talk first about what this sine theta means. Why is there more volume if theta is closest to, let's see, where do we get a peak in sine theta? We're gonna have a little peak in sine theta at, oh, the peak in sine theta happens at pi over 2, right? If this is sine theta and that's theta right there, the peak happens, okay, so we have a maximal value of volume when theta is pi over 2. And that's because if I have a small theta, let's draw ourselves a little sketch of a small theta. A small theta is going to have a z-axis right here and some vector, and this is our theta, and it's a very small value. That's going to be a very small ring. Right? However, if we have a large theta, I guess what I mean is a theta near pi over 2, then assuming my r is the same value, there's r right there, then I'm going to have a much larger ring. In fact, the length of the ring is going to be linear in sine of theta. Isn't it? As sine of theta increases, then we get a longer ring. So that makes sense. There's more possibility, there's more stuff at some volume that's located at theta is about pi over 2. Much more than there would be. In fact, the volume at theta equals 0 is none. That would be straight up. There's no volume there, none at all. Okay. And the other thing we need to make sense of is what's this r square business here? You've got yourself not just linear in r, but not even cubic, because it's like, maybe cubic would be nice to explain, because it's a volume. But the r square has to do with this, and that is that if you're at the center of this guy right here, there is no volume. There is no volume element that's trapped in right there. But as you increase, now I'm talking about